Hello there, ladies and gentlemen. Welcome to another exciting edition of HO Chemistry Flipped Classroom. This is Mr. Los. Today we're going to talk about electrolytic cells. I'm sure you're excited about that. Mr. Dog is here. He's excited. I think we should definitely all wave, say hello to Mr. Dog. Hello, Mr. Dog. How are you doing today? I even turned the right direction. That is more challenging than it appears. Anyway, so let's jump right into it. The big thing we need to do right off the bat here is we've been talking about galvanic cells. We need to compare and contrast with electrolytic cells and just get some of the differences. The huge overall difference is that galvanic cells use spontaneous chemical reactions to generate electric energy or generate electric current, whereas electrolytic cells are a non-spontaneous reaction, and by very definition of being a non-spontaneous reaction, they actually require a constant power source. So that's the huge difference between the two. And why would you want to use something that requires power or a non-spontaneous reaction? There's a few reasons. Electroplating, purifying metals, recovering elements from aqueous solutions. We're going to talk about all these, but that's the huge, biggest difference over here. We have two diagrams here. I'm not really going to talk about this much, but long story short, in a galvanic cell, electrons in this case travel from here to here. So they're going from Fe to Cu plus 2 ions in solution. If we wanted to make the electrons go in the opposite direction, that would be an electrolytic cell. That would require a battery or some other power source. You know, you can actually think of a battery as kind of an electron pump. It just kind of makes electrons go in places they quote unquote don't want to go. So that's what we, that would be one quick overview comparison of a galvanic and electrolytic cells. So electrolytic cell basics, what does that word mean? Well, if we break it down, electrolysis, it means, electro means electricity, obviously, lysis means split, so we're splitting something via electricity. Usually what we're doing is we're taking some sort of compound and breaking it back down into its elements. And again, these are non-spontaneous reactions that require an external power source. So some of the details, again, similarities and differences between the two types of cells. Oxidation at the anode, reduction at the cathode, that is the same as in a galvanic cell. However, the cathode is considered negative in this type of cell and the anode is positive. And yes, this is another one of these little confusing bits of terminology that comes up in this unit. In an electrolytic cell, the cathode and anode are given opposite signs. The cathode is negative and the anode is positive in an electrolytic cell. That is opposite in a galvanic cell. Why is that the case? Well, we can try to help. We can try to understand. You know, here's Mr. Dog here. He's going to help us walk us through and calm our minds as we think about it. I have a galvanic cell up here, an electrolytic cell down here, and a galvanic cell, remember, is something like a battery. So we are interested in the wire. So if we're a happy little fellow here who's living up in the wire, for our point of view here in the wire, electrons are coming from this direction. So to us, this seems negative, this side over here, and this seems positive because that's where the electrons are going. So from the point of view of the wire, this is negative, this is positive, this is the anode, and this is the cathode. So on the other hand, though, with a electrolytic cell, we are more interested in what's going on in the solution, because that's what a galvanic cell is for. This is a battery, we're supplying this power, but we want something to happen in this solution. So if we're another happy little fellow here who's living in the solution, so electrons are coming down from this direction, right? So if you are in this solution, if you're a positive ion in the solution, you're going to be attracted to where the electrons are coming from. So from the point of view of the solution, this seems like the negative electrode, and then therefore this one would be the positive electrode. So this is the cathode, which is where reduction happens, which is negative in this type of cell. This is the anode, this is where oxidation happens, which is the anode, but it's considered positive in this type of cell. So you can think about it, the electrons are going here, so that's why this is negative, and the electrons are leaving from this way, so it's kind of a lack of electrons. It's what's making that thing positive. So negative ions are going to be attracted to this. In both types of cells, cations go towards the cathode and anions go towards the anode. It's just we've switched the signs that we assign to the anode and cathode. They're opposite. Another big difference that you might notice is that in an electrolytic cell, the electrodes are in the same container usually, whereas in the galvanic cell they are separated into two different half cells. So that's another difference between them. This is the same really for both types of cells. Electrons travel through the wires, whereas ions in solution are going to carry the charge between electrodes. So that's the same in both. Another thing that's the same in both is that cations travel towards the cathode and anions travel towards the anode, as I mentioned. However, what's going to happen a lot of the times is the positive cations are going to get reduced back to the elemental form in an electrolytic cell, and then the anions are going to lose electrons and go back to an elemental form at the anode. So we're taking a compound and actually producing elements from it, which is not what happens in a galvanic or voltaic cell. Another thing that we need to know, and make sure you take note of this, is the notation that is used with these lines. These lines represent a battery, and in this particular one right here, this is actually labeled as positive and negative. That will not always be the case. Like it might, just show you this and expect you to know that this is the positive one and this is the negative one. So that's something you just have to remember. I've heard somebody say how to remember it is that this longer one could be broken up into a plus sign. I don't know. That sort of makes sense, but, or maybe, I don't know. Whatever. The longer one's the positive one, the shorter one's the negative. It's like if you're eating an ice cream cone or whatever. More is better, right? More is positive. So if it's bigger, that's positive. Maybe that's a good way to remember it. But yeah, you do need to know the notation there. And again, this is an electrolytic cell. They're in the same container. This is the positive one. This is the negative one. So this is the cathode in this case. This is the anode, sorry, which is the positive one in this type of cell, and this is the cathode, which is the negative one. So what we're going to talk about first in terms of electrolysis is the electrolysis of a molten salt. Molten, that means hot, like hot lava. So taking an ionic solid which have high melting points. You can't do electrolysis on a solid ionic compound because, as we've discussed several times, solid ionic compounds don't conduct electricity. So you do need to melt it. You're going to have to get it really hot and break it into freely moving ions. So then ionic solids are made of positive and negative ions, and when you're doing electrolysis in a molten salt, you're going to reduce the positive ion back to the elemental form. So we're not going to watch this video right now. Maybe we'll watch it in class, but for example, this would be composed of Li plus ions and Cl minus ions, lithium chloride would be, and we're going to reduce that lithium back to the uncharged elemental lithium, and that's a huge change. And then we're also going to oxidize this this chloride ion back into elemental chlorine. Again, huge change when that happens. There's a big difference between chloride ions and elemental chlorine. And our little electrons over here. So yeah, there's the ionic crystal lattice if you're having a little bit of trouble visualizing it. We do have to melt the ionic solid and break that down. That's what molten means. We're going to get it really hot. We're going to melt it. In the case of molten NaCl, very similar to the lithium chloride that we were just looking at. There's no water in here, and it's not a salt water solution. That's another thing that we're going to talk about later. But if we've just got pure NaCl in here, so we have our battery. This is basically would be showing several batteries in solution, or sorry, in series that are mounted up together. We could ask ourselves, what's the positive end of this and what's the negative end of this based upon this notation? That's the positive and that's the negative one. The longer one's positive and the shorter one is negative. So this is the positive electrode here, and this is the negative electrode here. So the positive electrode in this kind of cell is the anode, and the negative one is the cathode. We have oxidation at the anode, so chloride ions are being oxidized back to uncharged elemental chlorine, and sodium ions at the cathode are being reduced back to elemental sodium. This is in fact how we get the actual elemental sodium and chlorine, if we need to use it for various purposes, is they get it from actually doing electrolysis on NaCl. So that's where the source of that is. So you may have seen or know that you could buy, for example, some small cheap metal ring that's gold. It's not pure gold, but they've taken some sort of metal and they've plated gold around it. Super thin coating of gold. So we can plate a thin film of expensive metals and the less expensive ones, and we could take like a necklace that could be relatively cheap gold necklace, gold necklace, right, that's in fact only gold plated. And so it could be sold for much more cheaply than at 100% gold. So what you want to do is the metal, the thing that you want to plate that with you want to put it into a solution that has ions of the metal that you want to plate. And then you put that metal at the cathode, because cathode is where the reduction happens. That's the negative one in this type of cell. And so those metal ions are going to be reduced. And when they are reduced, what they'll do is, if your electrode is made of the metal you're trying to plate, they'll plate themselves right onto that metal and coat themselves around it. And if I haven't already, I'm definitely going to show you an example of this in class. So as I mentioned, the cathode is hooked to the negative terminal of the power source. So here's a very simple animation. This is kind of the opposite. Well, no, this actually, never mind. This is exactly what you'd want to do. If you wanted to plate an iron in silver, for example, you could have a silver anode, you could have an iron cathode, and as the silver is oxidized, now would be there's already silver ions in solution from the silver nitrate solution we got going here. So those silver ions are going to plate themselves onto the Fe. This is kind of exaggerated because you would lose mass at the anode here, because the silver metal that's making up the anode is getting oxidized and going to Ag+, and then the Ag+ ions are getting reduced, and then so we plate a nice thin coating of silver metal on the iron, and so we've got this thing that looks silver, but it's actually only made of cheaper. It looks silver, but it actually is mostly made of cheaper iron, and it's kind of exaggerated in that the plating of silver here would be very, very, very thin and very inexpensive. It's looked larger than it really would be in real life in this little diagram, but you kind of get the idea. So there are some things that we need to talk about that was going to influence the amount of product that is made when we are electroplating something. And this one should be pretty obvious. If you have your little setup right here, basically what I'm talking about is, if we have a little setup like this, what is going to influence exactly how much silver gets plated on this, or whatever metal we're trying to plate? What's going to influence that? Hopefully it's obvious that time is going to influence that. The longer you let the thing sit, the more metal it's going to plate. That's very simple, and it's a direct relationship. If you run it twice as long, you're going to plate twice as much metal. Also the amperage. So we can sort of think of the amperage as how many electrons are passing through the whole setup in a given amount of time. And again, this is a direct proportion. So if you have double the amperage, that means you're pumping twice as many electrons through here, and that means you're going to plate twice as much metal, or whatever it is. If you cut the amperage in half, you're going to plate half as much. It's going to be a simple direct relationship there with the amperage. Another factor that's a little bit more subtle is the charge of the ion. If you have silver ions and you have, for example, in a different situation, that's supposed to be a U, you have Cu+2 ions. If you're trying to plate silver in one case and you're trying to plate Cu+2 in another case, the silver only needs to gain one electron to become regular elemental silver, whereas the copper needs 2 electrons. So given everything being identical, if we're trying to plate silver in one case and copper in another case, same amperage, same time, same everything, we're going to plate twice as much silver because it requires half as many electrons. And again, that one is a little more subtle, but basically the greater the charge of the metal ion, the less is going to be plated in a given amount of time, because it takes more electrons to turn it back into the elemental thing. So that's it, guys. I spared no expense and time here. I got some word art going for you here. Lovely stuff. Really, let's take a good look at the word art. If you're not throwing some word art in your stuff every now and again, maybe you should. But we're going to stop right now. There's some more complicated stuff, definitely, that we're going to get into here when we talk about this. But for now, we'll call it good. Thanks for watching, and we'll see you next time.